So we continue with the study of the frequency response of transistor amplifiers. Last time we had started looking at this circuit and we had studied the low frequency response of this circuit, and first we had derived or analyzed the DC conditions of the circuit, and these are the values we had got. And for the low, okay, so this is the circuit, the small signal circuit, including all the capacitances. And for the low frequency response, we had ignored C pi and C mu and analyzed the circuit with CE. This lecture will see the effect of C pi and C mu, which affect the high frequency response, as we had seen last time. And we'll assume CE to be a short circuit because at high frequencies, CE behaves as a short circuit. So if CE is a short circuit, this is the small signal circuit we'll get. So let's quickly look here. So if this emitter node is grounded because CE being shorted, then what we are left off with is what is on the top, which is here. So now we need to, well, our goal is now to solve this circuit, including C pi and C mu. So here are the nodal equations. So there are two nodes, VB and VO. Vs is a given voltage. And so if we write a nodal equation at VB, we'll get 1, 2, 3, 4 terms. VB minus Vs over Rs, VB over R pi, SC pi VB for this, and SC mu, VB minus VO for the capacitor C mu. And if we multiply out by Rs R pi and combine terms, then we'll get this. And if we write a KCL at the output node, so we'll get 3 terms, VO by RC, GM VBE, which is just GM VBE because VE is 0, and VO minus VB into SC mu. So that is here, and then we multiply out by RC and combine terms, and we get this equation. So of course you must sit and derive these yourselves. So I guess this is a difference between doing this in class and in an online or a PowerPoint lecture, that it is not feasible or doesn't make sense to sit and derive this in the PowerPoint, but you have to sit and do these yourselves. So you must do that. So we get two equations, two unknowns, VB, VO. So the usual method is to find VB in terms of VO from the second equation, substitute that in the first, and find VO over Vs in the first equation. So I'm not going through this derivation like I had said last time also. You must, and eventually end up with this big equation at the end. And again, this is written in a specific form. So you look at this, there is a constant term here and there is a rational fraction here. The numerator is a polynomial whose constant term is 1. Similarly, the denominator is a polynomial of second order whose constant term is 1. The reason for writing it in this form, so this is a simpler way of writing this. So I've said 1 minus s by z, 1 plus s into this whole thing is a, plus s squared into this whole thing is b. So we can write it like this. The reason for writing it in this form is that for frequencies low frequencies, this s becomes j omega, and if omega is small, then all these three terms become small compared to 1, and then this becomes the mid-band gain. So writing it in this forms enables us to see directly the mid-band gain, which incidentally is what we had derived for the same circuit when we had discussed this circuit without the capacitance, is GMRC into R pi by R pi plus Rs. So this is the form of this transfer function. So as we can see, this transfer function has 1 0 in the numerator and 2 poles because the denominator is a quadratic. Of course, we want to study this transfer function and find what are the actual frequencies and then draw a Bode plot. So the first thing we want to do is find the roots of this polynomial, because those will become the two poles of the transfer function. So we can find the poles simply by solving this quadratic. But there is a nice simpler method of finding the roots. So let's discuss this now. So let us say 1 plus as plus bs squared can be written as in terms of its two poles, say p1 and p2. So given this form with this constant term being 1, we can write this as 1 plus s by p1 into 1 plus s by p2. And if we expand this out, we'll get 1 plus s into 1 by p1 plus 1 by p2 plus s squared by p1 p2. Now, suppose we assume that the poles frequencies, these pole frequencies, are what is called as spread far apart. That means that if P1 is much less than P2 in its value, and this is a case in many amplifier circuits, a large number of amplifier circuits have this property, and that is why this approximation is possible. And so if this is a case, if P1 is much less than P2, then we say 1 by P1 is much greater than 1 by P2. And then here, if 1 by P1 is much greater than 1 by P2, then we can neglect 1 by P2. And we get only 1 by P1. So we can write this as 1 plus s by P1 plus s squared by P1 P2. And now, without solving the quadratic, we can say, well, A is equal to 1 by P1 and B is equal to 1 by P1 P2, and 1 by P1 being A, this is A by P2, and so P1 can be approximately written as 1 by A and P2 as A over B. Because we know A and B, we've got the two roots of the quadratic without solving the quadratic. Now quadratics of course are easy to solve, but this method works even for higher order polynomials. I'm leaving this to you to just do this again. Let us say for a cubic, so it's a cs cubed, and you do 1 plus s by p3, expand this out and derive expressions, approximate expressions for p1, p2 and p3, assuming that p1 is much less than p2 and p2 is much less than p3. So then this becomes a nice simple method of finding approximately the poles of the transfer function. But there is another reason for doing this. It is not merely ease of calculation, because calculators and computers will take care. I think most of your calculators find roots of cubics also and all that. So this approximation really doesn't have as much value simply to approximate the roots. It has a different purpose also. The purpose is it gives us insights into the behavior of the circuit. So let's write this out. So let's go back to the transfer. So this is a transfer function. So 1 plus s into A. So A is this big thing and B is this thing. So if we were to write the poles approximately, we'll say P1 is approximately 1 by A, which is that big thing here. And now if we look at this, we know that GMRC is usually large, 100, 200, like that. C pi, C mu typically are of the same order, although C mu is slightly smaller, but same order, a few picofarads each. So we see that this GMRC C mu term will dominate in this first term, this C pi, and the 1 can be ignored. And then if we compare this with this, we say that again, because of this GM, this term will dominate compared to this term. And therefore we can write P1 as approximately 1 by GMRC C mu RS parallel R pi. And if we do this, we can write P2 with A as this, as it turns out everything cancels except GM by C pi. Now this is useful because this tells us that by the way, P1 is the minus 3 dB frequency, because there are two poles and this pole is a smaller one. So at P1, the low frequency gain AVM will start falling. So this also is called the minus 3 dB frequency. It is also called the dominant pole. So now we have an expression for the dominant pole. So now we can study this and think, and when we are designing a circuit and if we are asked to design for a specific upper cutoff frequency, a specific minus 3 dB frequency, then we can look at this expression and design to meet the specification for P1. So we can say, well, we need a certain value of RC and a certain value of GM. C mu and RS will typically be given to us, but GM, RC and R pi can be designed to meet the requirement for P1. This is the advantage of making this approximation. It allows us to do educated and informed design. Similarly, P2 is this, and we'll see the significance of P2 later on, I think maybe after a couple of lectures. But for now, it is important to see that we have an expression, approximate, but we have an expression for P2, which can be used to design. Okay, let's put numbers now. So we've already done the numbers. So they are all there in that for second slide of this presentation. I'm not going through the details. You can, you should actually do these calculations yourself. But the Z turns out to be 6.4, so 40 gigaradians and then 6.4 gigahertz. And A turns out to be, so by the way, A has the unit of time, RC, right? A is some R times some C, turns out to be 210 nanoseconds, and B is RC squared, so it is turns out to be 20 nanoseconds squared. And so P1 is 1 by A, and it turns out to be 760 kilohertz. P2 approximately turns out to be 1.7 gigahertz. So now if you look at these two numbers, we can confirm that P1 is much less than P2, at least 1,000 times, more than 1,000 times less than P2. The gain we've already seen before is minus 200, which is 46 dB in magnitude. So so let's draw the Bode plot of this. So we have two poles and one zero. So we write this transfer function. Now we've written it in terms of j omega and then jf, because f is more intuitive, the gigahertz. So these are gigahertz, these are gigaradians. So this is omega, this is f. So we can write the transfer function as AVM 1 minus jf by 6.4 giga, 760 kilo, 1.6 giga. So we see that the two pole frequencies are smaller than the zero frequency. The zero frequency occurs last. Okay, and we've studied Bode plots of simple transfer function. So I'm just drawing it here. So let's quickly kind of study this. So the low frequency gain is 46 dB. So for frequency is so this is the lowest frequency of the three. So frequency is much less than 760K. We can ignore all these three terms, and this whole thing will be simply 1. And so we get a gain of 46 dB. So the gain is a constant 46 dB. At 760K, the first pole is encountered, and after the first pole, and we've studied this before, the gain will start falling at 20 dB per decade. So after 760K, the gain starts falling at 760 dB per decade. Then the second pole comes at 1.7 giga. After the second pole, the denominator becomes f squared. And so on a log scale, the slope will double, the square will become twice, and so gain starts falling at minus 40 dB per decade. Then the zero comes at 6.4 giga. These are of course very closely spaced, about only 4 times, 5 times. After the zero, so frequency is much greater than 6.4 giga. These all three ones can be ignored. So this will be f divided by f squared. So it will be effectively 1 by f. So that is again minus 20 dB per decade. So after the 0, the slope becomes minus 20 dB per decade. So this is the overall Bode plot. Now, as I said, these are very closely spaced. So this piecewise linear plot that we've drawn is actually not going to be very accurate. If we draw the actual Bode plot, of course, we'll see a continuous plot with a minus 3B drop here at 760K. And then here it will kind of, you won't be able to see a nice 20 to 40 to 20 transition. It will be kind of continuous. But anyway, that's we are not really worried about that here right now. One more thing I have included here is, so you can see this is 46 dB. The gain is falling at 20 dB per decade, and this is at least 3 decades from 760K to 1.7 giga. So that means that from here to here, the gain is going to fall by 60 dB at least 3 decades. So my 46 to minus 46 minus 60 is minus 14 dB. So somewhere along the way, the gain will cross 0 dB. 0 dB is what? 0 dB means that the gain has become 1, unity. This gain was 200, the gain has become 1 here. And as we have seen in the very first lecture of this online lecture series, this is called a unity gain frequency. The frequency at which the gain becomes 1 is called the unity gain frequency. Okay. Which is also called the gain bandwidth product. And the designation is Ft or omega t depending on the 2 pi. And as we saw in the first recorded lecture, the last 3 slides of that lecture, this is an important quantity for a variety of reasons. Where 2 primary ones are, one is that the gain bandwidth product or the unity gain bandwidth remains constant under negative feedback. So when we put this amplifier under negative feedback, as you remember, reduces the gain. That gain 200 may be made 10 or 5 or whatever. The bandwidth of that negative feedback circuit will be higher, and the product of the gain and frequency with feedback, that product will be the same as the open loop product of gain bandwidth, which is the gain bandwidth product. Now, when we did this in the first lecture, we had assumed that the amplifier had a single pole. You can go back and look. Now in this circuit, our circuit, we have 2 poles and 1 0. So to find the unity gain bandwidth theoretically may be much more complicated, because theoretically what we should do is we should say, well, the magnitude of this gain becomes 1 and we must find the f with the equate 1 to the magnitude of this right hand side function and find f from that equation. And now you can see that that equation is not going to be simple, because there are 3 f's and the magnitudes will have square roots of 1 plus f squared by the frequency squared and so on. But given that for our specific transfer function, the unity gain frequency occurs much before the second pole and the 0, the fact that this will be the product of this gain and this 3 dB bandwidth is still approximately correct, as you can see that from this plot, that this part of the plot is unaffected by the second pole and the 0. So when the second pole and 0 appear much after the unity gain frequency, they tend to not affect the unity gain frequency. So mathematically we say that at the unity gain frequency, when the gain is 1, this term is still very small and this term is still very small, and therefore they can be ignored. And so these 2 terms can be ignored, and we effectively have a single pole transfer function. For example, you can see that 35 mega divided by 1.7 giga is a factor of about how much? 100, so 350, 3.5, about 50. So this is going to be 1 by 50, and when you, so 1 compared to 1 by 50 is much larger, so we ignore the 1 by 50, and similarly this one. And so we say that the gain bandwidth product of our circuit is simply AVM times P1, the first pole, which is this, and which is, so we just substitute for P1 and we find that it turns out to be 1 by C mu RS. Okay. So yeah, so this is kind of a comment looking into the future. We'll see that in order to ensure that amplifiers don't oscillate. Remember, we talked about oscillations, and we want to make sure that amplifiers don't oscillate. We'll see that the condition is that the second pole, everything second poles and zeros appear much after the unity gain bandwidth. So this is a realistic Bode plot for most amplifiers, and therefore this expression, the unity gain frequency being the gain times the 3 dB bandwidth, is correct for most amplifiers even though they have multiple poles and zeros. Okay. If RS is 0, okay, we assume that the source resistance was not 0. If we assume RS 0 and solve this circuit again, kind of solve means start from the beginning and derive the transfer function and find the frequency at which the gain of that transfer function becomes unity, we will find that that unity gain frequency with RS equal to 0 turns out to be Gm by C mu. So here in our circuit it is 1 by C mu RS. Of course there are approximations made, that's why it is 1 by C mu RS. If they are not made, there will be a GM also here, but you can see that if you want to. But the point is that if RS is 0 and we do this all over again, then we'll find that the unity gain frequency is Gm by C mu. This is sometimes called the intrinsic unity gain bandwidth or the unity gain frequency. Intrinsic because this is a function only of the transistor parameters. See, RS comes from the source, signal source, which is external to the transistor amplifier. This is a property of the transistor amplifier, and this is an important quantity because this tells us the highest frequency up to which we can obtain a gain from this circuit. Nothing higher, so this circuit can be used as an amplifier only up to the unity, this frequency. It cannot be used at a frequency higher. And so this defines the usefulness of this circuit for high frequency applications. Of course, remember, it is important to note here that this itself is a function of Gm, and Gm is a function of the DC collector current. So the unity gain frequency of a transistor amplifier does directly depend on the collector current that is flowing, which is interesting and important because what this is telling us is that if I want a higher unity gain frequency, or if I want an amplifier that can work at larger and larger frequencies, then my collector current must be larger and larger. And the DC collector current. And the DC collector current being larger and larger, of course, implies that the DC power consumption of that circuit is larger and larger. And this is I may have mentioned this in the last semester, this is a fundamental property of all electronic circuits, that if we want higher speed, we must dissipate more power. And the reason, the underlying physics of this is that if we want a higher speed, basically we want the capacitors in the circuit to charge and discharge faster, because speed is ultimately limited by capacitors. And if we want them to, well, yeah, if we want higher speed, we want to charge them faster, and if we want to charge them faster, means we must supply larger and larger currents, because capacitors charge with current, and so we must dissipate more and more power. So this is fundamental to electronic circuits. All right. Okay, now let's quickly look at the complete frequency response. By complete, I mean low plus high. So last lecture, we had derived the low frequency transfer function. So I'm just repeating it here. This lecture, we derived the high frequency transfer function. I'm just writing it in short form. And let's put it together. But before that, I wanted to mention that in the last lecture, I had made a mistake. This RS was missing in the expression for the low frequency transfer function. So please correct that. So I'm not, it's too much work to go back and record the lecture all over again. So I've not repeated the lecture, but I have changed the PowerPoint, the PDF of this that I have uploaded on LMS. So I've uploaded a second version of the last lecture that includes this RS. So please make note of this, this modification to the low frequency transfer function. So this is the short form of it. Okay, so this is a low frequency, this is the high frequency. We want to put it together and write the complete expression. And the complete expression is what? Just put these two together. So it is AVM, low frequency, high frequency. So this is the complete transfer function of our amplifier, including low as well as high frequencies. And we can write this in this form as we just saw, and we put numbers. These are from last time, these are from this time. So this is our complete transfer function numerically. And then this is the complete Bode plot. So this Bode plot we discussed today. This Bode plot we had discussed last time. So at low frequencies, 2 Hz, the gain starts falling and then it becomes constant when zero is encountered. So I put a dot here because this frequency range is very large, from 2-3 Hz to 700 kilohertz. So to indicate that this scale is broken in between, these are dotted lines. All right. Now it turns out that many times the quantity of interest for our amplifier is just to find the -3 dB frequencies, the higher and the lower 3 dB cutoff frequencies. So often all we want to know is this frequency and this frequency, because beyond these frequencies the gain starts falling. And it turns out that it is possible to estimate these frequencies without solving the small signal circuit. So what we've done in this lecture and the last is gone through the process of writing the small signal circuit, drawing the small signal circuit, writing the nodal equations and solving them, which is of course a very long process. I didn't, as I said, I'm not including the process in the PowerPoint, but it is long, the derivation is long, and it becomes longer as the amplifier becomes more complex. So next class or next lecture, we will study techniques of finding just the 3 dB frequencies without deriving the transfer function, without writing nodal equations at all. Just we'll draw the small signal circuit and we'll do something to find the 3 dB frequencies. For now, this is it.